variables that we've dealt with so far are initial position, final position, initial velocity, final velocity, acceleration, and time. And from those 6 variables, we can put together the different equations that we've talked about. Displacement, velocity, and acceleration. AP allows you to use an equation sheet, and on that they give some fundamental equations that you can use, and those are what we call the kinematic equations. I'm going to show you how we can use those and how we would identify which of those equations we're supposed to use based upon which variables are actually given in a single problem. The first equation on the sheet is just a different version of this single equation here for acceleration. That equation looks like this: velocity equals velocity initial plus acceleration times time. It comes from acceleration being velocity minus velocity initial over time, and simply rearranging it in terms of velocity. AP doesn't put a final velocity there, they just put velocity. To show you how you get to this main equation here, I would multiply each side by time. That cancels those times out. And then I would have acceleration times time equals velocity minus velocity initial. And then I would add velocity initial to both sides. And I get velocity equals velocity initial plus acceleration times time. This equation we would use in a circumstance where we don't have any of our positions. Our second equation is going to deal with when we don't have final velocity. That equation on a reference sheet is written as position, or final position, wherever you end up, is equal to my initial position plus velocity initial times time plus 1/2 acceleration times time squared. One thing that we can do with this is, let's imagine that there is 0 acceleration. So if acceleration in my problem is 0, that makes this entire part of the equation 0. And from that, I can then solve these for velocity. And so I would have final equals initial plus velocity times time. I could subtract my initial over and have position minus initial position equals velocity times time. And then I can divide each side by time. And that would give me velocity equals position minus initial position over time. So that's a way that, even though on our equation sheet we are not given our velocity equation, this is understood for a constant velocity. So I can use this equation here as acceleration is 0 to find what the velocity equation actually would be. In most problems though, we're going to have an acceleration in some form. So we can use this equation if we need to solve for final position, initial position, velocity, acceleration, or time if we don't have a final velocity. I will say it's hard to find time in this because we can form a quadratic equation. So there's typically another way or another equation that we can use besides this one if we need to solve for time and we have all these other variables. The last equation that you can use is this one, where we have our final velocity squared equals our initial velocity squared plus 2 times our acceleration multiplied by our final position minus our initial position. Or this here is our displacement, final minus initial. Right? This is an equation that we can use if the problem or the circumstance doesn't give us time. Right? We can solve for any of the other variables using all the others as being known if we just simply don't have time in our equation. What we'll do now is we'll work through a few examples of situations of where we would actually use each of these equations. Our first example is going to look at a problem that says, if we have an airplane that needs to reach a velocity of 27.8 meters per second to take off, and in doing so, the plane is going to accelerate at a rate of 2 meters per second squared. Is a 150 meter long runway long enough for that plane to reach the velocity needed? As well as, what is the minimum length of the runway required? So if the 150 meters is long enough, great. What's the shortest that the runway could actually be to achieve this 27.8 meters per second? Let's take a look at how we might set this problem up using identifying the variables that we have and then also identifying which equation we're going to use. So first thing we're going to do is we're going to identify the variables that we have in this problem. Our initial position is going to be 0. We're going to say we're starting at the very end of the runway. So here's our runway, here's our 0 point. We know our final position is going to be 150 meters. Initial position, final position, 150. Our initial velocity is 0. Our plane is starting here at rest. Our final velocity needs to be 27.8 meters per second, and we know an acceleration equal to 2.0 meters per second squared. The one variable we don't have in this problem is we don't have time. So what I need to do then is identify which of these equations am I going to use. If I look at this, this one has time, so I can't use this equation. This one also has time, so I can't use this equation. So what I'm going to do is I'm going to use this third equation to solve this problem. Is 150 meters long enough? So what I'm going to solve for is we know what our final velocity needs to be, but this is really what we're trying to figure out. If I travel 150 meters at 2 meters per second squared with an acceleration, am I going to be able to achieve the 27.8 meters per second that I need? So, setting this problem up, velocity squared equals velocity initial squared plus 2 acceleration times displacement. This is what I'm solving for, so it's already set up for what I need. So my final answer is just going to be a square root of this, 0 plus 2 times 2. My final position is 150 minus 0, square root of that. So we get 4 times 150, square root of that. That's the square root of 600, which is going to give me 24.5 meters per second. So what that tells me is 150 meters long enough. The answer is no. It's not going to be long enough. I'm not going to achieve a final velocity of 27.8, which is what I need. So let's move on to the second part of the question. The second part of the question asks for what is the minimum length. So with this question now, I again know my initial position. That's 0. Now I'm trying to find my final position. That's really what I'm looking for. My initial velocity is also going to be 0. My final velocity is going to be the desired velocity of 27.8. And my acceleration is again going to be 2. I again don't have time in this problem, so the one equation that I'm going to use is this one here. I'm left with velocity squared equals velocity initial squared plus 2 times my displacement, which I'm going to write it out like this. And really what we're trying to solve for is we're trying to solve for this position here, right? So I'm going to wait to plug in numbers, and we're actually going to work through this just with the variables that are here, right? So in doing so, first thing is I'm going to try to get x by itself. I'm going to subtract velocity initial squared from each side. And that's going to give me velocity squared minus the initial velocity squared equals 2. Whoopsie, forgot my acceleration there. Very common mistake. Acceleration, final, minus initial. Great. Again, we're trying to get x by itself. We're going to divide each side by 2a. That goes away. And I'm going to rewrite it so it's a little bit more of what we are used to. Final position minus initial position equals velocity squared minus initial velocity squared over 2 times my acceleration. And the last thing is I'm going to add my initial position. And that's what my final answer should look like. Now what I can do is I can plug in my numbers. My final velocity is 27.8 squared minus 0 over 2 times 2 plus 0. All right, so simplifying things, those go away, and we're left with 27.8 squared divided by 4. That gives me 193.2 meters. That is the minimum length that runway could be in order for that airplane to achieve a final velocity desired of 27.8 meters per second. Our second example is going to look at a situation where if we have a car sitting at a red light, again, draw my picture, right? The car's initial position is here and its initial velocity is 0. The light turns green, all of a sudden that car is going to speed up in this direction with an acceleration of 2 meters per second squared. And it's going to cross the intersection, which is 30 meters away. What I want to know is how long does it take to cross that intersection? So what we need to do is identify the variables that we have in this situation. My initial position is going to be 0. My final position is going to be 30 meters. My initial velocity is going to be 0. My final velocity, I don't know. My acceleration is going to be 2, and the time is what I'm looking for. That's my thing that I'm trying to figure out. How long does it take? So what I need to do then is identify which equation I'm going to use. So because we don't have this variable, this is the equation that we can use. Notice this one has final velocity as well as this one, so we have to use that second equation there. Writing this out, my equation looks like initial position plus velocity initial times time plus 1/2 acceleration times time squared. Now again, I said this one can be tricky to solve for time, but in this problem it actually works out based on the variables and the circumstances that we're given. For one, my initial position is 0, so we can ignore that. My initial velocity is also 0, and that tells me this problem that those two multiplied together are also 0, because 0 times anything is still 0. So I'm going to rewrite my equation as position equals 1/2 acceleration times squared. And again, we're looking for time. So I'm going to solve for that before I start plugging in numbers. To do that, I'm going to multiply each side by 2. That gets rid of my 1/2. So I have 2x equals acceleration times time squared. I'm going to divide by a. So I get t squared equals 2 final position over acceleration, and I'm going to square root. So my time is equal 2 times, now I can start plugging in my numbers, 30 over 2 square root. 2's cancel out, so really we're just left with the square root of 30, which is going to be 5.48 seconds. So that's the amount of time that we would use to cross that intersection, and that's an example of using that second equation. Our last example is going to look at, let's say we have a car that's accelerating at 3.5 meters per second squared. It's going to accelerate for 8.2 seconds, and it's going to end up traveling at the end at 185 meters per second. What was the initial velocity of the car before this acceleration actually took place? So filling in the things that I have, I don't know initial or final position, and I'm not worried about them. My initial velocity is what I'm trying to solve for. That's my goal. My final velocity is 185. My acceleration is 3.5, and my time is 8.2 seconds. So what I'm going to do is I'm going to use this first equation there in order to solve this problem. Here's an example of an image that I might draw just to help me. My initial velocity and time are both 0. I'm going to have an acceleration of 3.5, and I'm going to end at 185, 8.2 seconds later. With this problem, because I'm trying to solve for initial velocity, I'm going to work through my equation before I plug in, again, any numbers. To do that, I'm simply going to subtract acceleration and time from both sides. That gives me velocity minus acceleration times time equals my initial velocity. So I end at 185 minus 3.5 from my acceleration times 8.2. 3.5 times 8.2 is 28.7, and that is my initial velocity. 185 minus 28.7, and that's going to give me a value of 156.3. So those are 3 quick examples of how we would use each of those equations. Again, the best way to identify which equation you're going to use is by figuring out what are the variables that are known, what are the variables that I don't need, and then identifying which equation can satisfy that need.